High above the peaks of Mount Everest, a small machine hovers with a stability that defies the thin, freezing atmosphere, a testament to the engineering prowess of DJI. This single company has transformed what was once a fragile hobbyist toy into a global industrial tool that now commands over 70% of the world's civilian drone market. How can a device made of lightweight plastic and copper wire survive a fall from 300 feet or track a racing car at 60 miles per hour with perfect cinematic smoothness? It is a question that leads us into the heart of the most advanced robotics factories on the planet, where millions of units are birthed from a chaotic mix of raw earth and silicon. We are going deep inside the assembly lines of Shenzhen to reveal the secrets of how these modern marvels are constructed, from the microscopic soldering of flight controllers to the high-speed calibration of 3-axis stabilization systems. This is a journey through a manufacturing ecosystem so precise that a single dull solder joint or a microscopic imbalance in a motor rotor is treated as a catastrophic failure. Prepare to witness the extraordinary scale of a factory that produces enough hardware to redefine the low-altitude economy of the entire world. The story of this aerial revolution began in a messy dormitory at the Hong Kong University of Science and Technology. In the year 2005, a student named Frank Wang obsessed over the mechanics of flight, eventually presenting a graduation thesis focused on a flight control system for remote-controlled helicopters. Though his initial prototype crashed during its final presentation, the failure only sharpened his resolve to build a system that anyone could fly with ease. In 2006, he moved his operations to the industrial hub of Shenzhen with a modest goal and a small loan from his parents. The early years were brutal, characterized by a tiny staff working in a cramped storage room. But they were fueled by a perfectionist attitude that demanded every screw be tightened to an exact, unquantified feel based on years of experience. By the year 2009, the team had developed the milestone flight control system that allowed a machine to stabilize itself without user input. This breakthrough was famously proven when they captured the first ever drone footage of the peak of Mount Everest, a feat that went viral and signaled the end of the era of shaky, unstable aerial video. Before the first machine could take flight, the founders had to overcome the disconnect between academic theory and real-world business. In the early 2010s, the firm noticed a market shift where gimbals for multi-rotor unmanned aerial vehicles were selling 10 times faster than traditional helicopter flight controls. This pivot led to the launch of the Wukong multi-rotor control system in September of 2011, which became a massive hit due to its unmatched stability. The name of the brand translates to Great Frontier Innovations, a phrase derived from a Chinese expression suggesting that great ambitions have no boundaries. This philosophy drove the development of the Phantom series in 2013, an entry-level drone that was significantly more user-friendly than any other machine on the market. By transforming complex aerospace technology into a plug-and-play consumer product, the firm effectively kick-started the global market for civilian drones. Today, the humble beginnings in a storage room have evolved into a global empire, with a workforce of over 14,000 employees operating across North America, Europe, and Asia. Building a high-precision drone requires materials sourced from every corner of the globe, essentially utilizing half of the periodic table to achieve flight. The foundation of the power system lies in lithium-ion batteries, with the raw lithium often sourced from the vast salt lakes of Chile or the mines of Australia, which account for 45% of global production. Cobalt, essential for thermal stability in high-discharge cells, is primarily pulled from the earth in the Democratic Republic of Congo, while the natural graphite used for anodes is dominated by Chinese production at 76%. Beyond the chemical elements, The structural integrity of the airframe relies on high-grade carbon fiber and specialized thermoplastics chosen for their resistance to impact and their transparency to radio frequencies. The motors require silicon steel laminations as thin as 0.2 millimeters to reduce iron loss, and high-grade rounded magnets are custom forged to minimize the air gap between the rotor and the stator. Logistics networks move these tons of material daily, ensuring that the factory floor never runs dry of the essential ingredients needed for mass production. The structural skeleton of the larger industrial units often begins with bauxite ore, the primary source of aluminum found in a belt around the equator. This reddish clay-like soil is mined and then refined through the Bayer chemical process into alumina, or aluminum oxide, using a hot solution of caustic soda and lime. Once the alumina is dried into a white powder, it undergoes the Hall-Héroult electrolytic process to become pure aluminum metal. This metal is then cast into extrusion ingots or foundry alloys, which are shaped into the high-strength, lightweight frames necessary for professional-grade aircraft. For consumer-level drones, the process involves high-pressure injection molding of glass-filled polycarbonates, creating a chassis that is both flexible enough to survive a crash and rigid enough to support high-speed flight. Every gram of weight is meticulously calculated, as the ratio of propeller size to airframe weight determines the energy efficiency of the final product. By controlling the entire manufacturing process from the raw chemicals to the finished shell, the manufacturer ensures that the structural resonance of the aircraft does not interfere with the sensitive internal sensors. The scale of this sourcing operation is immense, as the factory benefits from direct access to the world's largest supply chain of electronic components in Shenzhen. This geographical advantage allows for a rapid prototyping cycle, where the time from a design iteration to a physical prototype is measured in days rather than weeks. Truckloads of specialized raw materials, from high-purity copper for motor windings to industrial-grade carbon fiber sheets, arrive at the facility around the clock to support 24/7 operations. Tens of millions of metric tons of bauxite and lithium are processed globally to feed the hunger of a market that is expected to grow tenfold by the year 2034. To maintain efficiency, the firm utilizes on-demand manufacturing and digital logistics services, reducing the need for massive inventories and allowing for quick iterations based on user feedback. This proximity to suppliers means that any new technological breakthrough can be integrated into the production line almost immediately, keeping the brand at the forefront of the global aerospace industry. The manufacturing process begins with the delivery of raw materials into the 25,000 square meter factory, where items are stored in climate-controlled silos and moved via automated conveyors. Before any assembly takes place, components are batch tested and cleaned to prevent any particulate contamination from entering the delicate electronic subsystems. The facility operates with a mix of high-tech automation and hands-on craftsmanship, employing between 1,300 and 1,500 workers at a single production site. Drones move through the line receiving instructions via quick response codes, which trigger the next phase of assembly or testing as the airframes begin to take their final shape. Inside the International Organization for Standardization certified clean rooms, the air is filtered to remove dust that could ruin a camera sensor or a sensitive gyroscope. This environment is so secure that even high-level managers must place their phones in opaque bags to prevent unauthorized photography of the proprietary assembly techniques. It is here that the transition from raw materials to an intelligent flying machine truly begins. The heart of the machine, the flight controller, is produced on surface mount technology lines, where robotic arms place thousands of microscopic components per hour onto printed circuit boards. Microcontrollers from the ST Microelectronics 32F4 series are the minimum requirement for the high-power computing tasks needed for sensorless, field-oriented control algorithms. These boards move through multi-zone reflow ovens, where lead-free solder paste is melted with a temperature tolerance of just 2 degrees to ensure perfect electrical connectivity. Once the soldering is complete, every board undergoes automatic optical inspection, where advanced vision systems check for bridged connections or cold joints. In the drone manufacturing world, a dull solder joint is a flight safety risk, so technicians are trained to ensure every connection is nice and shiny to guarantee thermal stability. This electronic brain contains the gyroscopes and accelerometers that detect orientation and movement, performing thousands of calculations per second to maintain a stable hover. This level of precision is what separates high-end drones from cheaper alternatives, as the reliability of the flight controller is the primary defense against a mid-air failure. The propulsion system is built around brushless direct current motors, which offer an 83% lower failure rate than traditional brushed motors. These motors utilize a stator composed of 28 layers of laminated silicon steel sheets, each as thin as 0.2 millimeters to reduce iron loss by 15%. The copper coils are wound with extreme precision, often utilizing manual winding for high-power professional units to achieve a higher density of copper and a peak efficiency of 92%. This winding quality directly affects motor torque and service life, as any imperfection can lead to overheating and eventual failure under heavy load. Surrounding the stator is the rotor, which contains high-grade rounded magnets specifically designed to minimize the air gap and create a more uniform magnetic field. To eliminate high-frequency vibrations that could blind the sensors, every rotor is tested on high-speed balancing machines, where minute amounts of balancing epoxy are added to the interior. This high-speed performance of the propulsion system allows the aircraft to reach 2,500 rotations per minute from a standstill in less than a third of a second. As the motors and airframe are united, the focus shifts to the 3-axis gimbal, the device that enables cinema-grade footage from a vibrating aerial platform. A gimbal consists of 3 small brushless motors controlling the pitch, roll, and yaw axes, compensating for the aircraft's movement at a rate of 400 adjustments per second. During assembly, the gimbal is placed on a precision-leveled surface where an auto-calibration sequence zeroes the roll and pitch sensors to ensure a perfectly horizontal horizon. High-resolution camera modules, featuring sensors as large as 4/3 of an inch, are integrated into these gimbals within cleanroom environments to prevent dust from entering the lens assembly. Technicians verify that the internal flex cables do not limit the rotation of the gimbal or become entangled during aggressive pans in high wind conditions. Logical stops and mechanical endpoints are programmed into the software to prevent the camera from accidentally viewing the drone's own landing gear during flight. This stabilization system is so advanced that it can compensate for movement in winds as strong as 60 miles per hour. Before a drone is cleared for distribution, it must pass a series of tests in an automated flight calibration cage that often measures 3 meters by 3 meters by 7 meters. Inside this netted environment, the drone scans a quick response code to initiate a validation sequence where it performs automated takeoffs, hovers, and landings without a pilot. The flight controller compares internal magnetic data from the compass with global positioning system signals to ensure there is no discrepancy that could lead to a flyaway. Vision systems are checked as the drone uses its omnidirectional binocular sensors to identify its position within the cage and avoid simulated obstacles. Propulsion power is tested by ramping the motors to 100% throttle while the unit is tethered, verifying that the current draw matches the expected power curve. If a unit shows even a minor instability or a sensor error, it is immediately flagged for recalibration or sent back to the assembly line for repair. This final flight check is the last line of defense, ensuring that every machine leaving the factory is ready for the rigors of real-world operation. The testing gauntlet continues in extreme weather chambers, where the drones are subjected to torrential rain and freezing temperatures to verify their ingress protection ratings. For industrial models like the Matrice series, these tests include operation in temperatures ranging from -35 degrees to 50 degrees Celsius. Wind tunnels are used to simulate high-velocity airflow, ensuring that the airframe and propellers can withstand wind resistance ratings of 12 meters per second for consumer models. Independent testing at the National Aeronautics and Space Administration Ames Research Center has even validated the aerodynamics of these units, measuring forces and moments on the rotors and airframes under varying speeds. Batteries are also put through their paces, with pressure mapping sensors used to detect any internal expansion that could indicate a defective vent or a failing cell. These batches undergo thermal runaway tests in dynamic pressure chambers to simulate low-pressure conditions at high altitudes. Only by surviving these extreme simulations can the manufacturer guarantee that its products will perform reliably from the humid jungles of Brazil to the icy plains of the Arctic. While these consumer and professional units are masterpieces of integration, they are part of a much larger family of machines that are currently redefining modern industry. For example, agricultural drones are built as flying tractors, capable of carrying 50-kilogram payloads and spraying vast fields 100 times faster than manual labor. These heavy-lift giants are constructed with specialized impeller pumps and phased-array radar systems to maintain precise heights over uneven terrain. Even in the world of high-speed racing, the assembly techniques vary wildly, with some hobbyists spending days building a single unit from scratch, yet the factory in Shenzhen has refined this process to a cycle time that is significantly shorter. The gap between a home-built drone and a factory-calibrated machine has never been wider, thanks to the massive investment in research and development that allows for such rapid iteration. This ability to move from a design concept to a finished prototype in just days is what keeps the brand at the pinnacle of the global aerospace market. And the final journey begins in the automated packaging wing of the facility. Once the quality control team gives the final approval, robotic arms carefully fold the airframe arms and propellers into their shipping positions, while the intelligent flight batteries are set to an auto-discharge storage level of roughly 60%. This prevents chemical degradation and ensures safety during long-distance transportation across the globe. Every drone is boxed with its remote controller, spare propellers, and documentation before being palletized and shrink-wrapped for distribution. The scale of the logistics network is massive, reaching over 100 countries through a combination of trucks, ships, and international cargo flights. High-level automation in the warehouses manages the flow of millions of units annually, ensuring that new models reach customers within days of their official release. The manufacturer has even begun to use its own delivery drones to transport tools and supplies across difficult terrain, ushering in a new era of the low-altitude economy. This seamless transition from a finished prototype to a global consumer product is the result of years of refinement in the Shenzhen industrial ecosystem. The economic significance of this manufacturing empire is unprecedented, as the firm currently owns approximately 70% of the global civilian drone market. In the year 2021, total sales reached 24 billion yuan, with revenues projected to surpass $55 billion by the year 2030. This growth contributes over $116 billion in economic value and supports nearly 450,000 jobs across the United States alone. In the agricultural sector, the company has shipped over 200,000 units in the year 2025 alone, a volume that is 100 times greater than it was just 10 years ago. These machines now treat over 500 million hectares of farmland worldwide, saving millions of tons of water and significantly reducing carbon emissions. By maintaining vertical integration and owning its own factories, the firm can sustain a competitive advantage that has driven many competitors out of the market. This dominance is not just about sales figures, but about the thousands of patents and technical innovations that have made high-precision flight accessible to everyone on the planet. We have traveled the full journey from the raw lithium mines and bauxite pits to the high-tech assembly lines where raw earth is transformed into a masterpiece of robotics. The story of the modern drone is one of persistent innovation, from a university thesis to a global industrial force that has redefined industries from filmmaking to search and rescue. Every smooth aerial shot and every precise agricultural spray is a result of the insane testing and assembly protocols we have witnessed today. This journey highlights how human ambition and robotic precision can conquer the challenges of the sky, turning complex aerospace technology into a tool we use every day. Now we want to hear from you. Do you use this type of technology in your home or for your work? And which feature do you think is the most important for the future of aviation? Let us know your thoughts in the comments below, and do not forget to like and subscribe as we tease our next look at the world of high-speed robotics. The journey of high-precision flight is only just beginning, and the factory in Shenzhen is already preparing for the next leap into the great frontier of innovation.